This video is going to set up all of the units and sign conventions and ways that we talk about and calculate transfer of energy. So internal energy, this overall energy that we're going to calculate, is a state function. So we should probably start by defining that. A state function means that the value depends only on the state of the system and not how you got there. So for internal energy to be a state function, this means what we're really looking at is a delta E, because we just want to look at the difference between the final state and the initial state, and it doesn't matter which way we got from the initial state to the final state, because this is a state function. So now the opposite of that, something where it does matter how you get there, that's a path function. Okay, so I think that we should look at an example of some state functions and path functions just so that you have this down. And to do so, we're going to use my absolutely terrible outline of the Missouri and Illinois state lines. And we are going to talk about taking a trip, just kind of, I don't know, St. Louis is about here. We're going to take a trip from St. Louis to Chicago. We'll put Chicago here. And talk about state and path functions related to this trip. So let's talk about how you could get from St. Louis to Chicago. So one option is that you could drive, and if you just take Interstate 55, you have a path that looks kind of like this. This is our trip option number one. You could still drive, but you could take Interstate 70. Let's do a different color. And then head north on 57, which will get you to Chicago. And let's say you are not interested in driving, but you want to take a plane. It'll be a pretty straight path. It'll be a little bit curved. We'll call that fly direct. And then let's just do one that is super out there. It's a color we haven't used. Guess we're going red. Okay. And let's say you're going to fly, but you got these really cheap tickets and you're going to fly, but you have a layover in something I can pretend to reach on this picture, Minneapolis. So you're going to fly from St. Louis to Minneapolis, which is probably still way over there, and then you're going to fly from Minneapolis to Chicago, which will still get you there. You probably would not have a very pleasant trip, but it would work. All right. In every single case, you started in St. Louis and you ended up in Chicago. But there are parts of this trip that are different depending on the path that you take to get there. So these are the path functions. So things like miles traveled will be different for every trip. Probably the money that you spend will be different for every trip. The time spent traveling will be different for every path that you take to get from one place to another. Now, the state functions, you still started in St. Louis and ended up in Chicago. So things like change in altitude overall are the same. And honestly, your overall change in altitude is probably not much because I think they're both pretty close to sea level. Your change in latitude would be different. Or not be different, would be the same for every trip because you have the latitude of St. Louis and the latitude of Chicago. Change in longitude, right? We could add this in too. Okay. State functions versus path functions. I hope this example helps. So now let's look at this with some actual reactions. So I have a reminder to start out with, which is just our change in internal energy is just E final minus E initial. Now, we have special names for those things when we're looking at an actual reaction, and these are not new to you, but we can just substitute it in and say that we're looking at the energy of the products, which is the final state, minus the energy of the reactants. So what I want to look at for an example, I have two reactions here. If you look closely, you can see that they're reversed of each other. So my first reaction is carbon solid plus O2 gas going to CO2. And then my second reaction on the right is CO2 turning into carbon solid and O2 gas. So if I take the products and the reactants and assign them an energy. Now we have ways that we are actually going to be able to do this and calculate this related to composition, mostly because they're calculated at specific temperatures. I can plot these on an energy diagram. So I'm going to have my energy diagram and the sort of collective energy of my reactants. It's going to be here, right? These are in this reaction, they're the reactants. So it's carbon and oxygen. And then the energy of the CO2 is here. And the identities of these components don't change from reaction to reaction, so their energies are going to stay the same. Now, what is different is that in my reaction on the left, this carbon and oxygen are my reactants, and CO2 is my product. So when this reaction runs, it goes from reactants to products. So my E final minus E initial is going to give me a delta E that is negative. In my reaction on the right, the CO2 is the reactant. So when my reaction runs from reactants to products, when I calculate a delta E, I get a positive value. So in either case, we want to know where does the energy go or where does it come from, right? This reaction on the left, it's a negative value. This is giving off energy. On the right, it's absorbing energy as it goes. So in the case on the left, right, we had two components that we were defining, the system and the surroundings. So let's look at that for both of these. And on the left, it gives off energy. So my system is giving off energy. That energy is flowing from the system into the surroundings. So my surroundings will have a positive energy because they're absorbing everything. In the other case, my reaction is absorbing energy, and it is absorbing that energy from the surroundings. So the energy is flowing from the surroundings into the system. So the delta E for the surroundings is negative. So because of the first law of thermodynamics, we can't create or destroy anything. The delta E for the system will always be equal in magnitude and opposite in sign to the delta E for the surroundings. Okay, so the methods by which this energy is transferred, the two that we are looking at are heat and work. So in every single case, we will have the system, we will have the surroundings, and between the two of them, we will have some exchange of work, which we represent with the letter W, and we will have some exchange of heat, which we represent with a lowercase q. Not what you were expecting, but we use a lowercase q for heat. So the work could be transferred in one direction, the heat in another. It all depends on the very specific system that you're looking at. But in every case, because of the first law of thermodynamics, the overall change in energy is going to be equal to heat plus work. And what you will find as a convention in pretty much every reading you look at, there's no subscript for this delta E. So we just had that delta E with a subscript of system is equal to the opposite of delta E with a subscript of surroundings. Here, the convention tends to be that we drop the subscript. But what we mean by this is the system. So we are just focusing on what's happening to the system and looking at the heat and work that are being done on or by the system. And we could very easily turn around and take that for the surroundings as long as we take the opposite sign. But when you see this specific equation, it is for the system. So, I want to really briefly touch on the units that you will see here, right? We need energy units, and the ones that you are used to seeing are things like joules, right, which we use a capital J for. Or, a joule is really small, so we'll see kilojoules quite often. You will now also see things like calorie. And so that is a lowercase c on calorie, and 1 calorie is equal to 4.184 joules. Now you may also see a calorie with a capital C, just to make things extra confusing. That's right, capital C, calorie, which is 1 kilocalorie, so 1K lowercase c, AL. So now this would be equal to 4,184 joules. And so these big C calories, these are the types of calories that you see on food labels. So if you see something that's labeled as 100 calories, well, it's really 100 kilocalories if you're using the lowercase c one. So it's really like 100,000 calories. All right. A last random one that we'll see a little bit when it comes to things like electricity is a kilowatt hour. So it's a kWh. And so a kilowatt hour is 3.60 times 10 to the 6th joules. Just to give you an idea of how small a joule is. All right, now the last thing that we need are sign conventions, which is basically, how do I know if my heat is positive or negative, if my work is positive or negative, and then what does it mean when the internal energy is positive or negative? So for heat, right, which remember we're doing with a Q, if you have a positive value for heat, it means the system gains or absorbs thermal energy. If you have a negative sign for heat, well, it's the opposite. The system loses thermal energy. For work, let's put a little divider in here. A positive value for work is work done on the system. A negative value for work is work done by the system. So the trick here is that you just have to watch out if the problem is starting to define things in terms of the surroundings, because work done on the surroundings was done by the system. So the wording is extremely important. And then with this, it's a crazy line. Sorry, I know you won't see it, but I had to erase it. We combine those two together to get our change in internal energy, right? If we overall have a positive value for internal energy, we're talking about energy flowing into the system. And negative is energy flowing out of the system. So, like I mentioned, you may be given this information in terms of the surroundings, and then you'll need to adjust your signs accordingly. So, let's do an example with this to show what it would look like. And our sample problem says a system releases 622 kilojoules of heat and does 105 kilojoules of work on the surroundings. What is the change in internal energy? All right, so Q, well, magnitude, we know that it's 622 kilojoules, and if the system gives off that much heat, then the sign should be negative. And work, we know that the magnitude is 105 kilojoules, and work done on the surroundings is work done by the system, so this is a negative. And both have units of kilojoules, so, all right, both have units of kilojoules, so I am good to just add these together. And delta E equals Q, which is negative 622 kilojoules, plus W, which is negative 105 kilojoules, which is negative 727 kilojoules.